Okay, let's dive right into this explainer and explore the ultimate cosmic mystery, the place where the fundamental laws of our universe literally collide. We're talking about the black hole information paradox. It's this massive puzzle that's forced the brightest minds in physics to question the very fabric of reality. We're pitting general relativity against quantum mechanics in a heavyweight battle where, honestly, something absolutely has to give.
To make sense of this physics crime scene, here's our roadmap for today. First, the laws of black holes. Second, the information paradox. Third, the firewall problem. Fourth, the page curve. And finally, number 5, islands and phase transitions. Let's just jump right in.
Section 1. The laws of black holes. Gravity meets heat. To understand how black holes break the rules, we first need to know exactly what rules they're actually playing by.
So, what actually happens to information when it falls into a black hole? This is the fundamental question. It's the one that's kept physicists awake for decades, challenging everything we know about the universe. See, in quantum mechanics, there's this strict rule called unitarity. It basically guarantees that information about the quantum state of a system is never irretrievably lost. But black holes, with their completely inescapable event horizons, well, they seem perfectly designed to test this absolute limit.
Before we talk about that missing information, though, we need to get one thing straight. Black holes aren't just empty voids of space. They actually have entropy, and it's directly tied to their surface area. Now, classical black holes were originally thought to have no microstates, meaning they were supposedly completely smooth and featureless. But to comply with the laws of thermodynamics, they must actually be hiding an enormous number of internal states. In fact, the math shows us the entropy of a black hole is directly proportional to the area of its event horizon.
To really grasp this, let's think about everyday thermodynamics. If you're to throw a cup of hot tea straight into a black hole, the tea's entropy seems to just vanish from the observable universe, right? But the generalized second law steps in and guarantees that the black hole's event horizon area increases to perfectly make up for that loss. So the total entropy of the universe, meaning all the stuff outside plus the black hole itself, never goes down. The black hole is effectively storing that thermodynamic information right on its surface.
Imagine dangling a fishing pole near the event horizon. The massive tension you'd feel on the line represents the surface gravity, and mathematically, that translates directly to the black hole's temperature. And we're talking about a true physical temperature here. General relativity's equations perfectly mirror the laws of thermodynamics, which totally sets the stage for a spectacular collision with quantum mechanics.
Which brings us to Section 2, the information paradox. Quantum reality breaks. Now that we've set up the rules, let's watch how things transition into a deeply unsettling quantum reality.
The Vaidya model diagrams the birth of a black hole from a collapsing shell of matter, trapping absolutely everything inside. In this Penrose diagram, that red line is the infalling matter collapsing at the speed of light. Everything above that line is officially trapped behind the event horizon. From the outside, it looks like a one-way street. Stuff goes in, and it seemingly never, ever comes out.
But here is the massive twist. Stephen Hawking proved that black holes actually radiate heat and slowly evaporate. And this raises the really alarming question of where that original cup of tea information goes when the black hole completely disappears. This is Hawking radiation. Over an unimaginably long time, the black hole shrinks, radiating its mass away into the surrounding thermal bath. If the black hole fully evaporates, what happens to the information of the star that formed it, or that cup of tea we threw in? If it's just gone, well, quantum mechanics is entirely broken.
So let's look at Section 3, the firewall problem, a terrifying paradox. Because trying to rescue this lost information creates an absolute physical nightmare in the math.
To understand this paradox, we have to talk about quantum entanglement. This is where particles become invisibly connected and share information instantly, no matter the distance. It's a concept Einstein famously disliked, dubbing it spooky action at a distance. But here's the thing. Hawking radiation isn't just random heat. It's created when entangled particle pairs are separated right at the event horizon. One falls in, the other escapes. For the information to ultimately escape the black hole as radiation, the outgoing particles must be entangled with the radiation that was already emitted in the past.
And this is where a strict rule called the monogamy of entanglement forces a huge crisis. To have a smooth event horizon, which is the equivalence principle, an escaping particle has to be entangled with its partner that's falling in. But to save the information, which is unitarity, it also must be entangled with past radiation. The problem? Quantum mechanics strictly forbids a particle from being fully entangled with two separate systems at the exact same time. It just can't happen. Something has to give.
Enter physicist Joseph Polchinski. He suggested that if we give up the equivalence principle to save the information, a literal firewall of energy must exist exactly at the event horizon to break that entanglement. In order to preserve quantum mechanics and save the information, the smooth connection between the inside and outside of the black hole has to be violently severed. This means anyone falling in wouldn't just float through peacefully, they'd be instantly incinerated by an infinitely hot wall of fire.
Crazy, right? Let's move to section 4, the page curve, rescuing information. Let's see how modern theoretical physics builds a mathematical life raft to track information without burning up Einstein's theories.
When we map this out, the first law of entanglement shows us something totally fascinating. The entanglement temperature is surprisingly negative while the black hole deposits information, and then it turns positive later when it releases it. Before a critical moment known as the page time, the black hole loses energy while the entanglement entropy of the radiation actually increases. This creates this bizarre thermodynamic state of negative entanglement temperature. It fundamentally proves that quantum information acts dynamically, carrying a highly specific energetic signature as the black hole evolves.
By tracking this shifting entanglement, the page curve mathematically rescues our missing information. It shows that the evaporation process is indeed unitary, meaning information is not lost. Initially, the entropy of the radiation goes up as entangled Hawking particles escape. But exactly at the page time, which is about halfway through the black hole's life, the curve suddenly flips. The entropy starts going down. This means the newly emitted radiation is highly entangled with the early radiation, carrying out the exact information of whatever originally fell in.
Okay, final stretch, section 5, islands and phase transitions, mathematical miracles. We have the page curve now, but how exactly does the black hole actually achieve this?
Well, physicists discover that after a certain point, that page time we just talked about, we actually have to include these bizarre interior regions called islands to correctly calculate the escaping information. This is a massive revelation. To figure out the true entropy of the radiation outside, the math demands we include a specific disconnected region deep inside the black hole. It implies that part of the black hole's interior is somehow secretly part of the exterior radiation. Space-time and quantum entanglement are completely, inextricably woven together here.
But what if the black hole doesn't just slowly leak information? What if instead it hits a critical mass threshold as it evaporates? In models like the evaporating BTZ black hole in anti-de Sitter space, we see that thermodynamics can suddenly shift. As the black hole slowly bleeds mass, its temperature and pressure dynamics inch closer and closer to a tipping point. And when the mass drops to a specific fraction, it doesn't just quietly fade away.
In this incredible scenario, the black hole undergoes a massive phase transition. Imagine water suddenly flashing into steam. When the black hole reaches that critical threshold, it spontaneously transitions into pure, empty spacetime. It's a true quantum jump. All the missing information it was holding is instantly and violently released back into the universe, completely bypassing that slow leak of Hawking radiation.
So what does this sudden release of information mean for the ultimate, undiscovered theory of quantum gravity? As we watch the most extreme objects in the universe bend our concepts of thermodynamics and quantum mechanics to their absolute breaking points, we really have to ask what profound cosmic secrets these firewalls and phase transitions are going to reveal next. Whether information escapes through tiny, continuous Hawking leaks connected by hidden quantum islands, or bursts out in sudden, massive phase transitions, one thing is absolutely certain. Black holes are not just cosmic trash cans. They're the ultimate quantum hard drives of the universe. So the next time you look up at the night sky, ask yourself, if space-time itself can literally jump and phase transition, what else is reality hiding from us?